So, in the last class we looked at the geometry of void spaces, which we call interstitial void spaces or interstices in the closed packed structures. One was tetrahedral void, another was an octahedral void. We saw the geometry, the sizes of the small spheres which can probably sit in there in metallic crystals. Having had a look at that, we talked of the solid solutions, interstitial solid solutions and substitutional solid solutions, talked about the Hume-Rodri rules, and then we also told you that solid solutions can also be random or ordered solid solutions. Now, continuing with stacking of spheres of different sizes, we go over to the ionic crystals, where again the bond is non-directional in nature, but the two ions are of different sizes. So, continuing with the assumption that ions are the hard spheres, we can talk about them as cations and anions. But in my discussion, what is a cation, what is an anion, that is what has to be very clear to you. It is not necessarily what you studied in chemistry. One is going to be a smaller ion, other is going to be a bigger ion. The one which is a smaller ion, I call it cation. The one which is a bigger ion, I call it anion. This by and large satisfies the definition you had in chemistry, that positively charged ions are cations and negatively charged ions are anions. I have some exceptions here to my definition and comparison to the chemistry. These are some of the elements from the group 1: potassium, rubidium, cesium and francium. Their ionic radii are 1.33, 1.48, 1.65, 1.75 respectively, and I have taken two of them from group 7, fluorine and chlorine. 1.33 angstrom, 1.81 angstrom. Bromine, iodine will be still bigger than that. So, you can see that fluorine, which is the smallest here, is equivalent to potassium in size, but smaller than these three elements, these three ions. So, if there is a compound of rubidium and fluorine, my definition would be this is cation, this is anion. This is a smaller ion, this is a bigger ion, right? But even if I go to chlorine, find chlorine is bigger than all of them, and these will be all cations and chlorine will be the anion. So, these 2-3 examples which are the exceptions, otherwise my definition is not going to clash with chemistry definition. Why I am talking about the smaller ion, the bigger ion shall become clear to you when I start talking about the geometry. Then we define the coordination number or the ligancy as the number of bigger spheres surrounding a smaller sphere in the center. In other words, number of anions surrounding a central cation. That is going to be the coordination number or the ligancy. Well, we shall work this out when we look at the geometry by working out the numbers of these bigger spheres surrounding the smaller sphere in the center. While looking at the geometry, we shall work this out, we shall talk about these numbers. But before we go over to that, we have to talk about certain rules of stacking spheres which are of different sizes because they are also electrically charged. One is positively charged, other is negatively charged. My rules are maintaining the stability in the configuration, and we are talking about the local coordination, local arrangement, and there I have to satisfy the electrostatic attraction. So I define anions and cations touch each other. That's the definition of an ionic bond, and our assumption that ions are hard spheres. When two hard spheres, positively charged, negatively charged, attract each other, they touch each other, they form a bond. The bond length is the radius of the anion plus the radius of the cation, center to center distance. That's why we say anions touch cations and cations touch anions, because that's how the ionic bond is formed. So in other words, a bigger ion touches a smaller ion and a smaller ion in turn touches the bigger ion. Anions generally will not touch. We'll show you the geometry, because anions are also charged. Even if it is negatively charged, this charge density on the surface would be smaller because it's a bigger one as compared to the charge density on the cation, which is a smaller one. Therefore, the repulsion between them may not be very strong, but it will be repulsion because they are same charges. So they usually will not touch. However, there could be limiting situations while talking about the geometry in which anions can be made to just come as close as their diameters, and they just start touching each other. That's just a limiting case, that's not the general situation. And thirdly, as many anions, the bigger ions, will surround the central smaller ion, the cation, as possible, what the space can provide, the geometry can provide for, so that the electrostatic energy is minimized. There is a maximum possible reduction there. So these are the rules on which my stacking of spheres of different sizes is going to be based on, so that we start looking at the short range arrangement first and then go over to the long range arrangement. Here I show you a certain coordination. There is a central sphere, the blue one, surrounded by the bigger spheres, the anions, 3 of them. Anion is touching cation, cation is touching anion, cation is touching this anion, and they are all touching all 3 of them. But anions are not touching anions. There is a gap between them, there is separation between them. This is what I mean by anions touch cations and cations touch anions, and anions in general do not touch each other. The central cation would like to surround itself with as many bigger anions as possible. How many it can, that's what we are going to look at. Now in this case, we also said that what is a limiting situation when anions just begin to touch. That is the limiting situation, when anions touch anions, and anions are also touching cation, cation is touching anion, and cation is touching this anion, but anions also touching each other. This is the limiting situation, or this is the limiting case, right? That is what I talk about as the limiting case. And this is going to be my general case. That is how mostly we will find the stacking of spheres of different sizes, which are charged spheres, anions and cations in general. But this is a situation not acceptable. Let us see what is the situation. Anions are touching anions. The central cation is so small that the hole what is formed is rattling in that hole. Either at the most it can be close to two of them like I have shown here, or it is slightly displaced, it will be close to only one. So in this local arrangement, cation is touching anion only once or twice, but it is not touching all the three. And anions are also touching anions, which is not generally the situation. So this is not an acceptable case for coordination 3. For coordination 3, this is the most general situation, and that is the limiting situation, right. In this situation, it is either touching one or at the most two anions. So this would be as good as if I have an anion, a cation, and an anion touching like this, and again maybe another cation, another anion. So every cation has only two anions around it. It does not have three. So this does not go for the coordination 3, it goes for coordination 2 only, this situation. So this is what about the coordination number 3. Same is the situation for coordination number 4, 2, 6, 8, 12, whatever we have. Those are the situations which will be similar in nature. This is what I mean by when I said what are the rules in which we are going to decide this. Now from this it is very clear, if I define the radius of the cation as RC and define the radius of the anion as RA, then this is a certain value which can be worked out for the limiting case. If it is greater than that, this is possible. If it is less than that, this is the situation, this coordination is not possible. So limiting case when I work out shall give me the radius ratio of the cation to anion, which is the smallest value for that coordination, right. For this triangle, can you work it out? It is an equilateral triangle. This perpendicular drawn from this onto this side of the triangle passes through this center of gravity, and 2/3 of this distance is this radius of anion plus radius of cation. If this is 2, this is 1 in this right angle triangle, that side is under root 3. So I get, and that distance 2/3 is 2/3 of under root 3 of r, which is the radius of the, or sorry, radius of anion, let us put it like this, right. 2/3 under root 3 of the radius of the anion, that is this distance, and this is equal to radius of the anion plus radius of the cation, and under root 3 will make it 2 by under root 3 here. So if I get the radius of cation from here, it will be 2 divided by under root 3 minus 1 of radius of the anion. You can simplify this, it will be 0.155. So, if the radius ratio is smaller than 0.155, this is the situation. Coordination is 2. If it is 0.155, it is the limiting situation for coordination 3. If it is greater than 0.155, this is the coordination 3. This is the meaning of those 3 conditions which I placed in understanding the geometry. Is it clear? Yes, please.
Coordinate, suppose if you go more number of coordinations, is it always planar coordination or it may be?
I'm coming to that. I have not finished my talk. I'm going to the next. And because after all my crystals are 3-dimensional in nature, they are not planes like this, right? We'll come to that. This is a local arrangement. We have to make the 3-dimensional arrangement. We'll come to that. Right. In here now I place these limiting situations for coordination 2. It will be 0. Anions would touch anion. It means the size of the cation is 0 as compared to the size of the anion. There is no such situation. So, limiting case is only, as I said, just the limiting case. General case would be RC by RA greater than 0 but less than 0.155. I shall get the legancy 2, which means the coordination is linear, just now which I showed you in the picture. Then coordination 3 also I showed you, starting from the limiting case of 0.155 goes up to 0.225. That is what I want to talk about, the triangular configuration, which is a plane. Now configuration with legancy 4, that means central cation is surrounded by the 4 anions. This geometry we have seen in the last class. If I make a tetrahedral void in FCC or HCP, whatever sphere I put in there is going to get bonded to the 4 neighboring anions, and those 4 are touching themselves. Therefore, that becomes a legancy 4 and configuration becomes tetrahedral. And what did we find the size of sphere that we can fit in the tetrahedral void? 0.225 of the parent atom. Now this parent atom in our case is anion. So the radius ratio, cation to anion ratio would become 0.225. That's a limiting situation here and gives me the tetrahedral coordination. Now this will go on expanding the cation size and anion will go separate out, right. This will go on till it is possible for the 5th anion to come around it from somewhere, some direction. But whenever we are able to put the 5th, we are also able to put the 6th simultaneously. And that situation also we saw in the last class. When we make an octahedral hole in a closed packed structure, means the anions are just touching and you have a hole in the middle where I can put a small sphere which is the cation, and that size is 0.414. So radius ratio becomes 0.414. I have 6 neighbors to the central sphere, smaller sphere. These 6 are the anions and configuration is octahedral. This is where my friends sometimes confuse, because here the word comes octa. Octahedral means this, the configuration is forming 8 faces which are equilateral triangles. That does not mean there are 8 neighbors to the central cation. Number of neighbors, the number of anions surrounding central cation is 6, right. So do not get confused with that, and 0.414 is a limiting situation. These two we have already seen in the last class. Now we shall see the next one. When I keep on now separating the anions, because my size of the cation is increasing, it will go on till it is possible to bring 8 of them close to it, not the 7. When 8 come, this also is very simple to understand. You have seen a simple cubic structure, they just touch each other, and the body center will be the place where the central cation can sit. If it sits there, it will be touching all the 8 corner, right. So that is the situation. In that, if you find out body diagonal is 1.732 under root 3, so radius ratio you will find out to be 0.732. That's what it is. I am not working it out in the class, you do it yourself. It is 0.732. That's when the central sphere touches the 8 anions in the corners of a cube, and we call it a cubic coordination. Now you keep on increasing the size of the cation again, anions will go separate out, but this situation will go on till it is possible to bring in 12 neighbors when the size of all the ions is the same or all the spheres is the same. That is what we have already seen in the metallic crystals FCC or FCP. Now if the cation size becomes bigger than that, my definition will change. Anion would become cation, cation would become anion, and it will fall somewhere here, right. Why I define the smaller ion as cation should become clear to you now. So if it becomes bigger, it will have to fall in back somewhere there. Is that right? Okay. Having had a look at the short range arrangement, I have to develop an ionic crystal. It must be the 3-dimensional crystal, and to get the 3-dimensional crystal, I have to make this local arrangement same everywhere. I have to repeat this in such a way that I get the 3-dimensional crystal. However, electrical neutrality has to be maintained, because no ionic crystal is electrically charged. Take sodium chloride, it's not charged, you don't touch it, you don't get any shock, because it's electrically neutral, right. But when I make the radius ratio for sodium chloride, we'll be talking about is about 0.53 if I am not wrong, around there. From your list, what will you say suggest? Octahedral coordination. Means there is a sodium ion in the middle and 6 chlorine ions around it. Each chlorine ion has one negative charge, -6. Sodium ion is +1. So net charge on the local group is -5. If I repeat this -5 charge, it will be ultimately charged material. So I have to ensure that this is not electrically charged. It has to be electrically neutral. Second thing is, the bond between sodium ion, chlorine ion, or a cation and anion is non-directional in nature. So I must stack them as closely as possible. Okay. And then I am talking of the spheres which are charged spheres. If suppose I have 2 spheres, one is smaller, one is bigger, and both have the same charge, the charge density on the spherical surface of the smaller sphere would be more, and charge density on the bigger sphere will be less. So repulsion between cation would be very large, because the charge density on the surface is very high. As a result, I must avoid cation repulsion, and this becomes very dominant when the charge on the cation is more than 3. I have to be very careful. We will see some of those structures. Now this is what we observe as far as local stacking is concerned in some of the well-known ionic crystals. Beryllium oxide, radius ratio we observe is 0.22. You predict from your table 3 or 4, because 0.225 is just for the 4, so just around there knocking, what we observe is 4. Silica is 0.29, you expect 4, you observe 4. This is also a covalent bond, spends most of the times, 50% time as covalent, 50% times ionic, and satisfies the conditions for both sp3 bonding as well as the radius ratio. It satisfies both of them. Al2O3, radius ratio is 0.36, you expect 4 but you observe 6 because a charge on the aluminum is +3. Magnesium oxide, you 0.46, you expect 6, you observe 6. TiO2 0.49, you expect 6, observe 6. Sodium chloride 0.53, expect 6, observe 6. So on and so forth. Calcium fluoride 0.73, which is very close to the limiting case 0.732, is you expect 6 or 8 but you get 8. Cesium chloride 0.93, expect 8, observe 8. So that's about the geometry. Except one or two exceptions, in this case only Al2O3 is the only exception really speaking, we observe whatever we have talked about. Now to make the long range arrangement where I have to ensure electrical neutrality, close packing, then whenever the valency on the cation is 1 or 2 usually, but at sometimes like aluminum I am talking about the 3 is also possible, we can do that. Coordination number or ligancy is 4 or 6, I am specifically talking about 4 or 6. Okay. The structures can be described in a very simple manner by the cubic close packing we talked about and the hexagonal close packing we talked about. This we have been talking about in last 2 classes. So it can be defined on that, and then whatever the tetrahedral voids and octahedral voids are formed, those are occupied by the cations depending upon what the ligancy is, whether it is a tetrahedral coordination or it is an octahedral coordination. Only one thing I have to be very clear about in this case, that FCC close packed structure, when we talked about, all the spheres were touching and central sphere was touching the neighboring 12 ones. Now when I make the FCC packing of anions, I have already stated in the beginning of the class, anions generally do not touch anions. When that happens, as if you made an FCC packing with spheres of radius, let us say r, and then reduce or replace those locations with spheres of radius 0.5 r or 0.6 r. So there is a space between them now. This is what I mean by FCC packing of anions or cubic close packing of anions. Anions are not touching anions. Similarly the hexagonal. So the close packed plane, when you look at, the spheres are not touching but the locations are similar to what we find in the close packed structure, right. That is what I mean by this when I talk about the consideration of the structure is as a cubic close packing or the hexagonal close packing, and the cations going into the tetrahedral voids or the octahedral voids depending upon what the ligancy is. A majority of your ionic crystals will be covered in this. Here is sodium chloride. These yellow spheres are the anions, which in this case are chlorine ions. The blue ones are the cations, the sodium ions. Coordination we have already seen is 6 octahedral coordination. In an FCC close packed structure, where are the octahedral holes located? Body center and the edge center. Very good. And see whether your cations are. Your cation, this one is in the body center. These 4 on the edge centers. This is on the edge center. 4. Again these 4 on the edge centers. There are 12 edges and 12 on the edge centers. 1 on the body center. And we have the chlorine ions and the 8 corners and these 6 phase centers, 4 here and 2 there. This is FCC of sodium ions. This is what I mean by FCC of sodium ions or FCC of chlorine ions, because I can also start from here and make the FCC of sodium ions. FCC of chlorine ions or the anions here is this, that anions are not touching, and what the holes formed between them are going to be same, regular octahedral holes and regular tetrahedral holes, because placements is the same that as in a cubic closed packed structure. So this octahedral hole is occupied by the cation, and this is the, now this itself becomes a long range arrangement. Why this itself becomes a long range arrangement? This is the unit cell which can repeat and is electrically neutral. Somebody would ask me, how is it electrically neutral?
Total number of sodium ions.
Number of sodium ions and number of chlorine ions in this FCC is equal, 4 and 4. From the FCC locations I get 4, from the H centers I get 3 sodium ions and body center gives me 1. So I have 4 cations and I have 4 anions. This is absolutely neutral. There is no electrical charge on it, and this can repeat, right? So this is how we can define.
Although anions are not touching each other, but cation and anions.
They have to touch. I have not shown it here. They are not. I have not shown them touching because I want to show you inside. I wanted to show you inside and the edges at the back. Therefore, I did not make it touching. If I make them touching, you can probably see the top, front, but you will not be able to see inside. This inside thing is what I wanted to show. Therefore, I made it open. Right? But this means what I am trying to say is radius of the chlorine ion plus the radius of the sodium ion becomes half the lattice parameter of the unit cell. Right? So, in here what you observe is radius of the cation plus radius of the anion is equal to lattice parameter A divided by 2. Right? And if you are talking this as a crystal which is FCC space lattice, motif also you can define is here. This is the motif. Chlorine ion and the sodium ion, and this motif is placed at every lattice point, on this lattice point, on this lattice point, right? You want to see on this lattice point, it's same, everywhere it is same, it's not different. So that's how you can define the space lattice and the basis for a sodium chloride structure. Next, we have talked about Al2O3, where we said that we observe 6, the coordination is that of 4 radius ratio. It forms hexagonal close packing of oxygen ions. If I look at the hexagonal unit cell and form a close packing of oxygen ions, how many oxygen ions do I have in hexagonal unit cell? I shall have, since I am making close packing, it should be 6 oxygen. And how many octahedral holes will I have? 6. But how many cations do I have? 4. For 3 oxygen I have 2. So therefore for 6 I shall have 4. So out of the 6 octahedral holes I have to use 4. I don't use all the 6, and these are staggered in the crystalline form of Al2O3. This is next hard material as after diamond, for where we cannot use diamond being very expensive, we use Al2O3. for grinding, polishing and other things. And that certain gemstones, they are also based on this Al2O3 structure only, but they are not pure Al2O3. When I add 3 to 5% of chromium ions, that means I am substituting 3 to 5% of aluminum ions by chromium ions, trivalent chromium ions replace the trivalent aluminum ions, I get ruby, which is red stone. It's one of the expensive stones. Well, this is also a very hard material. We use them in making jeweled bearings. No, of course, we have all electronic watches. We used to have mechanical watches where you write 17 jewels, 21 jewels. Those are the bearings in which the gears are rotating, and there are different gears of different ratios, so that the second needle moves, minute needle moves and hour needle moves, all those things are there. These bearings are used for that kind of thing. Blue sapphire, when we replace 3 to 5% by iron ions, the aluminum ions are substituted by iron ions, I get blue sapphire, which is also an expensive or semi-precious stone.
So again, this was substitutional solid solution.
It's a substitutional solid solution.
Can interstitial possible? There are two octahedral voids left unoccupied.
Well, what you are saying, can there be an interstitial solid solution in an ionic crystal? That would be a charged ion, the charges will be problem. These charges, if it is there, then charge has to be adjusted somewhere else. So some other ion has to be missing from its side. We shall talk about those kind of structures, just wait, a week later we will talk about that, right? These are called imperfections in the crystals. We will talk about those imperfections. Right now we are talking about perfect crystals, ideal crystals, okay? Then the another ionic crystal of interest to us is the Ab2O4 kind of is where oxygen is there, and A is a bivalent cation and B is a trivalent cation. These are spinels, in which case all the bivalent A ions go into the tetrahedral voids and all the trivalent B ions go into the octahedral voids, and oxygen forms cubic close packing. Okay, it forms a cubic close packing, that means FCC. In the FCC, I have 4 oxygen form the FCC unit cell. There are going to be 4 octahedral holes, but I am using only 2 of them. There are going to be 8 tetrahedral holes, but I am using only 1 of them. So repeating unit actually becomes bigger. It becomes 8 times the size of the unit cell, which has only 4 oxygen. And more important than spinel is the inverse spinel structures. These are magnetic materials which are called ferrites. Manganese ferrite, or you talk about zinc ferrite, or you talk about chromium ferrite, and so on and so forth. Here the bivalent ions is what, like zinc or chromium, but trivalent ions are iron. This is called inverse because the place of trivalent ions here is taken by the bivalent ions, and place of bivalent ions is taken by the trivalent ions. Like this, bivalent ions go into the octahedral voids. Here it was the trivalent ions going into the octahedral voids. And trivalent ions, half of them only go into the tetrahedral voids, because you need to notice here 1 tetrahedral void and 2 octahedral voids are occupied in one FCC unit cell. These are 2 out of 4, this is 1 out of 8. So number remains same even here, only 1/8 of the tetrahedral voids are occupied and 1/2 of the octahedral voids are occupied, one by this, other one by that. So 2 of them are occupied, 2 octahedral holes are occupied and 1 tetrahedral void is occupied. In here, 2 octahedral voids are occupied because trivalent ions are 2 in number and 1 tetrahedral void is occupied. So that remains the same. Inverse, because what was in tetrahedral void has gone into the octahedral void now. These are the ferrites, and we will talk about them when we come to the magnetic materials. We will talk about these structures there. Right, after these 4 or 6 coordination, we come to this coordination number 8. And in here I gave an example of cesium chloride. Radius ratio is 0.93. This is the cesium ion in the body center location and chlorine ions at the body corners of the cube. This is the short range arrangement, and this itself is electrically neutral if I make it a repeating unit, because these chlorine ions will be shared by 8 unit cells each. There is only one within this volume, and one cesium ion is within the volume, so cesium chloride becomes electrically neutral. Isolated, yes, it is charged, but when I repeat it, the repetition, this being the common one, that is get electrically neutral. Alright, that is the arrangement of coordination number 8. In here, from body center to the body corner, the distance is under root 3 by 2 of A, and this is equal to radius of cation plus radius of anion. Okay. So that is the arrangement which we have looked at in these structures. Now we shall talk about another crystalline arrangement where I have tetrahedral coordination as silica, SiO2. Charge on the silicon is +4. I have to maintain a greater distance between 2 silicon ions, because there is a very strong repulsion between them, and also I have to maintain the SiO2 composition as well as the neutrality. So in here, these are the tetrahedra. Let us consider the blue ones are the upright tetrahedra with apex being here on top, while these ones, grey ones, are the inverted ones. So that when I join an upright tetrahedron, upright means considering this as a plane, it is upright, okay, and inverted going behind this plane, the apex is going behind the plane. What we are doing is we are making the distance between this center and that center of the tetrahedral hole the longest possible distance. At any other position they will try to come closer. So that is the silicon which is the center of the tetrahedron, and corners of the tetrahedron are all oxygen. My formula is satisfied, and I get a sheet like this. I can make a similar sheet like that and put one over the other. So here it is upright, I will put here the inverted one of the second sheet. So corner to corner sharing takes place. That corner to corner sharing will be here, it will be here, it will be here, 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 here. When I go behind to continue, put this, the corner to corner sharing will take place with this one. The upright of that will coincide with this, this, that, this and that. So like that, 3-dimensional structure can be built up. Coordination, silicon being in this body center of the tetrahedron, the 4 corners of the tetrahedron gave me only 4 coordination. Each corner is common between 2 tetrahedra, Oxygen is half here and half there, and 4 oxygen corners, 4 halves of this makes it 2. So 4 corners oxygen, each corner giving half makes it 2 oxygen, and within the tetrahedron only 1 silicon is there. So SiO2 formula is satisfied. Is it clear? See, this is, I said 50% covalent, 50% ionic. Ionic structure, local arrangement is there. We can see tetrahedral arrangement, but it is so spacious arrangement. It's a lot of space here where you can put a lot of tetrahedra inside in this space. This is all vacant space, because if I bring in something there, there will be silicon will coming closer, and there will be a strong repulsion between silicon and silicon. And this is the hexagonal crystal of quartz. Quartz is used for various applications by engineers. One is that it has very low coefficient of thermal expansion. That is where we use it when we do not want any expansions taking place in some locations. Secondly, it is a piezoelectric material. Piezoelectric means when I apply a mechanical force, piezo is pressure, electrical field or a field is generated in the crystal, means ions displace themselves in such a way there is a dipole formed, and once a dipole is formed there is an electric field generated. That is the use for this piezoelectric crystal, which is exploited in forming the load cells. It is exploited in lighters where you want discharge to take place, and that is the kind of applications we put the. Otherwise, being a very hard material, again it is used in jewel bearings. It is also used because of the piezoelectric behavior as a natural oscillator, which gives us the time on the watches. Quartz watches are using this as an oscillator. The application of an oscillator can be understood like this. Suppose this is a crystal, between these two plates which are charged. When the charge is applied or this voltage is applied, the crystal shrinks in size, so contact is broken. Then once the contact is broken, there is no field applied to the crystal, it comes back to its original shape. Once it comes to original shape, it touches the two plates again. The moment it touches, it shrinks in size. So that is how it is becoming behaving like an oscillator, and that gives us very accurate timings, because frequency is, natural frequency is well established, and that is what we are using in watches. But the use of this SiO2 for engineers is in the form of a non-crystalline state. Glasses, all glasses, window panes, windscreens, etc., they are made of a non-crystalline silica. It may have impurities in it, that we will see, but in non-crystalline state it is not periodically repeating arrangement. This array is not a regular hexagon. Sometimes it may have 7 around this, or it may have 5. So it is not a regular periodic arrangement, and silicon distance is becoming shorter some places, and that is what is usually done by the impurities when they are present. So that is a non-crystalline arrangement, and by and large when you melt silica and from the melting point try to solidify, it is very difficult for it to crystallize. It has to be a solidifying in a non-crystalline state. Liquid like structure solidifies, and what the impurities do, that we shall see next. Impurities which are present in glass, they lower the viscosity and make it softer. glass softening temperature or the glass transition temperature of the glass is lowered because its viscosity is lowering by the addition of impurities. We have seen crystalline and the non-crystalline form, but there is tetrahedral network. One tetrahedron is joined to another tetrahedron. They are all primary covalent bonds. Only when these primary covalent bonds are broken somewhere, I can try to lower the viscosity, and that's what the impurities are doing. Maybe we will be able to see that in this picture. Let's say I have added the impurity like soda, Na2O is the soda. Oxygen contributed by the soda goes on one corner of the silica tetrahedron. It sits on the one corner of the silica tetrahedron. So one extra oxygen is coming, you see, and therefore it breaks that oxygen corner which was shared. Now there is one oxygen extra, so they are all separated, and that becomes electrically charged. This also becomes electrically charged. The two sodium ions which you are adding, they go and sit close to them to neutralize that, because there is an attraction between negative charge ion and positive charge. So sodium ions sit there. Similarly, the lime, when it is added, calcium oxide, it breaks the tetrahedral bond at the corner of the tetrahedron. One extra oxygen comes there, and this calcium sits in between the two because of the electrostatic attraction. As a result, I am creating electrostatic attractions like this, but in turn I am breaking the tetrahedral network which continues infinitely in 3 dimensions at many places. As a result, the networks are becoming smaller and smaller. Smaller networks of tetrahedra are sitting there. One can translate with respect to other more easily, rather than if I have the whole thing as one single network. That is how the viscosity is coming down, or the temperature at which it is possible to make the translation between one network with the other network becomes lower, because there is a breaking of bond. More the impurities I add, more such corners would be created, lower will be the viscosity. Less the impurity I add, less corners like this would be there, so higher will be the viscosity. That's what we see in these glasses which we are using. We use Vicar. Vicar is more or less silica with small quantity of like 4% impurity, which is borax, boron trioxide, and 4% means it breaks only few places, the corners. The viscosity is not still very low. Softening temperature for such a glass is above 1100 degrees centigrade. Quartz around 1800 degrees centigrade fuses, but this is just about 1100 degrees centigrade, so it can fuse. But when I add more impurity to the tune of 20%, where 4% is soda and 14% is borax, I get Pyrex, which is you must have heard of the Pyrex wares in the market, they are available, and you must have heard of the hard glass test tubes. Yeah, they are made of Pyrex and contain about 80% silica. The fusing temperature, or they will fuse about 550 degrees centigrade. You see how come down 1800, 1100, come down to 550. Then you have window glasses, window panes, or soft glass test tubes, okay, where a lot of impurities in it, 14% soda, 9% lime, 4% magnesia, 1% alumina. And this window glass, window pane which we use, you can about 120 degrees centigrade, you can fuse it, right. So this is what, the more the impurities added, more corners are broken. More corners are broken means there are more large number of smaller tetrahedral networks and the smaller networks can move more easily than one huge big network, right? That's how the viscosity comes down in these materials. These additions of impurities is also called modifiers. In the glass, what we have added are the modifiers. They modify the viscosity. Right, so we shall close today and discuss the similar structures in the next class.